there.
Is there any other type of motion capture other than optical?
There is. I mean, there are those inertial devices that we talked about last time.
Oh, okay.
Yeah. So those ones are a bit more. They measure. It's hard for them to measure position, but they can measure velocity and acceleration. So you can backtrack and compute as long as you know the initial position, you can use velocity to track the positions over time. Yeah. Usually those are done in tandem with optical motion capture, actually. So probably the more advanced setups nowadays have both the cameras and the inertial trackers as well.
That makes sense. So I was just thinking about it. I was like, like there's audio motion.
That would be pretty cool though.
So I think that just gives you like the more precise velocity acceleration than you would probably get with the optical because there's just so much to like measure.
Exactly.
Okay.
Yeah. They're kind of opposites in the way because with optical motion capture, optical can track positions really well, but then to get velocities and accelerations, you have to take the derivative of the position signal, which can be pretty noisy. Whereas the inertial trackers, those are good for velocity acceleration. And so,
That means
mhm.
I did a book I wanted for birthday.
Oh.
This is it's a pirate book.
Nice.
The author went here. I thought was very interesting. That he went to Cal State Fullerton.
Went to
Yeah, like he went here. Yeah,
That's
I
awesome.
thought that because you remember I showed you my honors project.
Yeah,
Like,
yeah,
this
yeah.
book inspired one of the games that inspired my honors project.
Oh.
Like Monkey Island. They said this was the biggest influence.
Really?
And I was like, wait, what?
Wait, this book was pretty old then, or the
It's from like the late 80s.
okay.
Mhm.
Yeah, Monkey Island. I mean, if you follow gaming street,
Yeah.
everyone knows Monkey Island.
And I thought that was really cool that this
Yeah.
one, they said like this and Pirates of the Caribbean, the ride were the
Yeah.
influences on that. And I
Oh,
was
I-
like, that's really freaking cool that, because apparently this guy and his friends came up with the term steampunk as well. For like, that
Oh.
whole idea of like sci-fi fantasy.
Yeah,
I was like,
yeah.
yeah.
I
And
had
I
no
got
idea he went
creative
to.
writing minor here.
Yeah.
Never heard of these guys.
That's crazy. I had no idea he went to Cal State Fullerton.
Yeah,
That's really cool. So you just got some.
yeah, that was a birthday.
Nice,
That's
nice.
pretty good so far.
Nice, nice.
Yeah, I'm liking it. Pirates, you think there would be more good like books and stuff on
Yeah,
it?
yeah.
I haven't heard of much, but it's pretty interesting.
Pirate Life is always so fun. I feel like, especially with,
Yeah.
with Pirates of the Caribbean when that
Yes,
was
this
really
this
crazy.
goes into the fun of it, even though there's, sword slashing and all
Yeah.
that, but I like how moves the main characters with all the cursing. And
Yeah.
The most impressive insult you've ever heard.
Uh-huh.
And all the language is broken, but the insults are unimaginable. They can't conjugate, they can't make things correct, but they're very creative.
With the limited tools that they have.
Yeah. So far I'm liking it, because it's about a puppeteer who he goes to the Caribbean to reclaim a stolen inheritance that his uncle stole from him.
Yeah.
And then he gets captured by pirates
Uh-huh.
and ends up becoming a pirate.
Mm.
So is motion capture, is it really the same idea as like the 3D movies, but instead they just have like little trackers?
Yep. No, it's
Okay.
exactly the same. Yeah.
Because I never thought about it until just now, but when just reading the several cameras, I'm like, wait, that's how they did 3D. So,
Yeah.
okay.
Yep.
Interesting. Are we going to talk about how they determine like where to put them? Or
A little
what?
bit. Yeah.
Okay.
Yeah. That is really important. Yeah. There's no hard rule for it. So, there's no, guidelines for it.
For a lot, though.
Yeah. Yeah. The real answer is that it kind of depends on the motion, depends on the situation, but we'll talk about some good rules of thumb and kind of what to look out for. Mhm. All right, it's 4 o'clock. Let's go and get started. All right, good afternoon, everyone. How's everyone doing today? Good, hanging in there. Weather is cooling down. It's good. It's easier for me to sleep at night when it's cold, so I'm very glad that the weather's cooling down. Okay, so today the plan is we're just going to continue on with our lecture notes. So last time we introduced this idea of optical motion capture and how it can be used for biomechanical study. And so we'll go deeper into that today, talking about just some logistics of how you set it up, and we'll get a little bit into the calculations, but I think we'll do most of that on Wednesday. Okay. All right. Any questions I can answer before we get started for today? Okay. All right. So let's go ahead and pick up where we left off. Okay. So where we were last time is we were talking about this idea of optical motion capture. So, this idea of optical motion capture, I think, is becoming more and more, I think, recognizable to most people. I think most people kind of see its use in entertainment and making movies, video games, things like that. And that's certainly where most of the driving, most of the money is coming from. I was talking with someone in office hours last week that, the hard thing about doing science is that, there's not a lot of money that goes into doing science unless you can kind of sell it. But there's a lot of money in Hollywood. And so when Hollywood is interested in something, same thing as scientists are, then it helps them a lot because it helps to have Hollywood money. So the idea with optical motion capture, or I guess the motivation is, when we want to track human motion, so or any kind of biological motion, you know, the kind of the baseline of where we need to start is we need to be able to track what the different parts of the body are doing during different parts of the motion. Okay. So that's the motivation, right? And so, before when we were doing static analysis, this was not really a concern, just because with static analysis, it's very easy to kind of see, what position that they're in, because, if they're in a static position, we can kind of, walk around and kind of see exactly the exact angles that we need to. But there are some human motions or some biological motions that happen so quickly, it's hard for us to kind of track, everything that's going on at any given time. But all those small details matter a lot because, whether your elbow is at a certain angle versus another one, or, the exact, trajectory of your shoulder joint throughout the motion, that affects, what muscles are going to be activated, and that affects how much forces are going to be activated, your injury risk. And so, we need some kind of system to be able to track these things. And optical motion capture is one way to accomplish this. Okay. So basically the idea of optical motion capture is to attach all these little tracking devices, these reflective trackers on a person's body and capture their paths, capture their motions with, high definition cameras. Okay. So you've probably seen, actors or some or others, do this exact thing. And so, it's kind of a silly kind of costume. So they have to wear kind of a very kind of basically a jumpsuit that kind of clings to your skin very tightly. And then the outside of that suit is made of Velcro or some kind of sticky material where you attach these little white markers on them, right? And so visually, it kind of looks something like this. So you have a person that's, walking around and they have all these little markers attached to their bodies. Okay. And then on the side here, you have one or more cameras that are kind of, capturing the entire thing. Okay. And so the idea is that, if you place the markers in a careful enough location and you have enough cameras that, that can track it, for every marker, okay, provided that you've set up you have your setup well done, what you're going to get from this is a parametric set of coordinates, right? that can track the X, Y, Z positions of that tracker as a function of time, okay? That's in the most ideal situation. So ideally, you'd be able to track every single marker this way, but we'll discuss later that sometimes it's not as perfect. So just kind of in a nutshell, as a person moves, maybe some markers will be obscured from the camera because the person's body may get in the way, or maybe they are moving towards the camera, and so their exact motion is not really picked up that way, or maybe it's in a blind spot. So ideally this is what you want, but sometimes it's not as perfect at this, but the idea, but hopefully, you have enough cameras, you have enough markers on the body that you get enough data that you can reconstruct everything that you need to. Okay. And so for, if your goal is to do, just kind of body tracking for, maybe to move some kind of computer model for some kind of, movie or some kind of animation, you would kind of stop. This would kind of be where you would stop. So generally, for entertainment, to obtain kind of realistic motions, then basically artists will basically map the positions of these trackers to positions on some kind of three-dimensional model of some kind and use that for an animation somehow. But for biomechanical analysis, we actually have to take this a step further. Okay. Because what we're truly interested in is we're interested in the joint angle kinematics. Right? And so what I mean by that is, let's say that, you're going through a motion. So let me just kind of focus on, let's say that we have just kind of a shoulder and elbow joint right here. Okay. And so if we call the angle between the shoulder and the person's neck, we'll call that theta 1. Okay. The elbow joint, we'll call it theta 2. And we'll say that we have a wrist joint as well here. We'll call it theta 3. Okay. These are just three example angles. In reality, because some joints you're going to have multiple angles associated with them as well. The shoulder joint is one particular joint where you need three angles to fully kind of define its position. But the elbow joint is a hinge joint, and your wrist joint mostly a hinge joint as well. Okay. And so for biomechanical kinematics, we're not really interested in the positions of the trackers. We're interested in the angles of the person's joints as a person goes throughout the motion. Okay. So we want theta 1 as a function of t, theta 2 as a function of t, theta 3 as a function of t. Okay. And then by that same token, we also want their angular velocities. Okay. So d theta dt for all of them. Okay. And then also their accelerations as well. Right? It may not be 100% clear why we want this just yet, but once we do the next unit on inverse dynamics, it'll be clear why we want these ones instead of just the tracker positions. Okay. So there's a little bit of processing that needs to be done. And so that's of course what we're going to be talking about. How do we take tracker positions, and how do we back calculate joint angles from those? Okay. But that's generally the idea, and that's going to be kind of the that's basically what's going to dominate our discussion for this week of how do we take kind of raw motion tracking data where we have XYZ positions of the markers, and then how do we transform that into joint angle kinematics that we can use for calculations? Okay. All right. So that's kind of the idea, but you know, of course, the devil, you know, for this unit here, the devil is in the details, and so you know, there's a lot of devils this week. So you know, we'll be going over a lot of rotations, transformation matrices, vector algebra, so a lot of really good stuff this week. All right, any questions on this so far? Yeah.
Does that mean for like a movie, they would put the trackers different than for like a scientific?
Yes. Yeah. So for movies, I think you know, a lot of times you know, these trackers are used for CG. And so well, sometimes, you know, sometimes they're using these trackers to animate a human basically in animation, right? So like Pixar, I think. But a lot of times, you know, these trackers are used to animate non-human things. And so, you know, for instance, you know, for video games, you know, it's very common to have like a monster, like a four-legged monster or something like that. In order to get like a real realistic motion, they may have someone just don like a mocap suit and then pretend to be a monster. And so they may put the trackers differently based on where the critical joints or critical limbs are for that, you know, made up monster that they're trying to animate. But for these ones, you know, we, you know, for biomechanical analyses, you know, we're mostly interested in, you know, can we track this joint angle throughout the entire motion? And so, you know, accuracy is kind of more of an important thing rather than kind of an art thing. Yeah. Okay. All right. So let's get into some of the details. All right. So the way that this is kind of broken down, you know, we use kind of a similar mindset as our biostatics analysis, where we consider each body segment kind of individually. Okay. And so each segment of the body is considered to be completely rigid, right? And so they all kind of move together. So your lower arm all moves together, your upper arm all moves together, your torso all moves together. Of course, you know, there is some small variations to that. You know, we'll talk about, you know, if you place the markers on some soft tissue, you know, like some muscles or maybe on top of some fat, you know, those positions are kind of, you know, a little bit loose, but, you know, for the most part, your upper arm is considered a rigid body. Okay. And so to track the position and orientation of a rigid body, the minimum that you need is 3 non-collinear markers. So for each segment of the body that you're interested in tracking, you need to make sure you have at least 3 markers on there, okay? Now, granted, you know, each segment of the body is usually connected to another segment, and so it is possible to share a marker, and so you could have one marker that's part of one segment and another one that's part of another segment. And in fact, you know, this is very common when you have a very prominent joint. That's generally easy to pick up on the camera. So, you know, kind of the connection between the upper arm and the lower arm, as well as the connection between your thigh and your lower leg. Usually you'll have one marker that's either right at the elbow or right at the knee that's kind of shared between both segments. Right? And so, for example, if we have kind of the upper and lower arm, and I'm just going to draw them as just kind of oval blobs at this point. Okay. So to track the motion of this upper arm right here, you need 3 non-collinear markers. And so, non-collinear just means that they can't all exist on the same line, okay? And so you need at least 2 lines to kind of connect all these points together, okay? Okay. But then to track the lower arm, you need another 3 markers. But you can use the same one that's at the elbow, right? So the requirement is only 3 per segment. And so you may have one here, maybe one here. So this one right here is shared between the upper and lower, okay? All right, so once you have that, once you have the markers placed, now you need the cameras to pick up its, its location. So we're not going to get into the details of how a camera actually tracks these things, but in general, you can consider you can kind of think of it as each of these markers they're reflective, and so you can almost think of them as each as kind of a tiny light. And in fact, there are some trackers nowadays that might that might give off some small kind of infrared signal that can be picked up by certain cameras. So there's obviously a lot of really interesting technology there, but we'll for our purposes, we'll just assume that it works, okay? All right, but the most important thing is that you need to make sure that you have enough cameras to pick up its location, okay? And the reason for this is that, a camera, by itself can really only pick up a 2-dimensional image. Okay. Now, of course, when we're looking at a lot of pictures, we perceive that there's some depth into it, but there's not actually any depth there. It's just kind of how our brain kind of understands, how certain things are positioned from one another, and there's a lot of really interesting actually optical illusions that kind of play off this kind of understanding as well. But at its core, a camera can only capture a 2D image. And so if you wanted to track a marker and you wanted to track its 3-dimensional position as a function of time, that means you need to have at least 2 cameras. Okay. Okay. Let me kind of show you just an example here. So let's say that we have a body, okay, and we have one tracker that's right here. Okay. And just like above, we're interested in tracking the X, Y, Z Cartesian coordinates of this tracker as a function of time. Okay. So X of t, Y of t, and Z of t. Okay. Okay, so the bare minimum to get this is to set up 2 cameras. Okay. So let's say that we have one camera that's looking at the action from over here. So let's say this is camera 1. Okay. And then we'll have another camera that's capturing it from down here. Okay. So that'll be camera 2. Notice how they're perpendicular to each other. So one looking at it from the left, the other one's kind of looking at it from the bottom here. Okay. And overall, we're looking at this. This is kind of a top-down view, right? So we're looking at the room. We're looking at it from the ceiling. Okay. Another thing that we need some kind of reference point that's not going to move. That's within the frame of both cameras. Okay. So let me go ahead and put a star. Okay, so this would be our reference point. Okay. The reference point is really important because whenever you're measuring position, in reality, there's no such thing as absolute position of a certain body, right? whenever you describe position of something, it's always relative to something else, right? So your position sitting in this room, or, for those of you on Zoom, sitting in your own room is relative to, maybe your, I don't know, your kitchen or something like that, or relative to the library. And so same thing here. And so if we wanted to track the position of this tracker, we need some kind of reference point to track that from. Okay. All right. So let's take a look and see what the camera sees. So let's look at the view from camera 1. And let's say that we have a certain camera setup here where it obscures most of the body itself, and we only can see the reference point and the tracker. Okay. Okay. So the view from camera 1 would look something like this. And so based on the position of the reference point, we could position camera 1 so that the reference point is in the bottom left-hand corner of the screen. Okay. Now, if we were to put the tracker here, okay, that camera is able to see the tracker, and let's say that it's positioned right here. Okay. All right. And so relative to the position of the reference point, right? So the reference point is in the bottom left-hand side of the screen. Let's say that the distance from here to here is about 10 centimeters. Okay? And the distance from here to here is 30 centimeters. Okay? So these are measured relative to the room. So this is we don't have kind of a gigantic screen here. That's the physical distance, right? So of course, there's a little bit of conversion factor here where we kind of know exactly the dimensions of the room, we know the dimensions of the camera, okay? And so, based on those things, we're able to pick up, each pixel on the screen may be worth, maybe half a centimeter or something like that, okay? So these right here are actual physical dimensions. Okay. Okay, so that's the view from camera 1. And so if we look at the view from camera 2, right? So notice where I put that reference point. So that reference point is kind of right here, right? And that's very strategic because now this reference point is also going to show up in the bottom left of camera 2 as well. Okay. And so from here, let's say that we view the location of the tracker. Okay. So that dot there is the same tracker that's here in camera 1, but we're viewing at it from a different angle. Okay. Okay. So let's say that we measure these out. And so let's say the distance from here to here is 50 centimeters. Okay. And the distance from here to here is 30 centimeters. Okay. All right. So based on these views right here, and based on our measurements, we can come up with an XYZ position of that tracker, right? Now we have to define exactly which direction is the X direction. We have to define which direction is the Y direction, which direction is in the Z direction, okay? Okay. Usually there's some kind of reference frame where there's some kind of, if you're doing this in a biomechanics lab, usually they already kind of have something established there. But for our purposes, let's say that, let's say that this direction is the X direction going up. We'll say this direction is the Y direction. Okay. And then the Z direction is looking straight at us. Okay. Okay. And so if that's the case, if the positions are as follows, right? Then we know that this direction here is the X direction. You know, this direction here is the Z direction in the view of camera one. And then in the view of camera two, you know, this direction is the Y direction. And the dimension that both cameras sees is the Z direction going up and down. Okay. Okay. And so if we take the reference point as the origin, right? Okay. We can come up with an XYZ position of this marker based on our two views here. Okay. Okay. So first we have the X coordinate. So the X coordinate relative to the reference point is going to be 10 centimeters. Okay. The Y coordinate relative to the reference point is 50 centimeters. And the Z component, which is the height of the marker off the ground that we do see in both of our cameras, is 30 centimeters. Okay. Okay. So that's a very simple case, and so that's kind of an ideal case too, where you have two cameras perfectly perpendicular, that is with the perfectly positioned reference point. But that's kind of the idea, right? So each camera on its own can only do 2D images, and so in order to kind of position something in 3D, you need at least two camera angles. All right, any questions on this example here? Okay, good. So at least two. So at least two cameras are needed to position a tracker in 3D. Okay. They don't necessarily have to be perpendicular to each other, although that's kind of the simplest case. And of course, this example here kind of oversimplifies the optics too. And so, you have to kind of take into account that, when you view something out of a camera, same thing as your eyes too, there's kind of a conical field of view. And then the way that projects onto a 2D image, that there's some calculations there, but so we're ignoring most of that stuff. We're ignoring most of the details of this. But I just kind of want to make you aware of it. Okay. In reality, most motion capture setups are going to have more than one camera. In fact, a couple dozen cameras is actually not that uncommon too. And the reason for that is because, if you're interested in tracking human motion, a lot of times, the body itself is going to obscure some of the trackers, right? So if you imagine if you have a tracker that's on your hand and you have a camera that's in front of you, you can put your hand behind your back and that's suddenly going to obscure that view. Okay. So, for that reason, you may need some redundancy in your camera setup so that, if a certain camera, its view is blocked, maybe another camera can capture that, that motion as well. Okay. So, generally speaking, the more cameras that you have, the more accurate your motion capture is going to be. Okay. And of course, all of these, relative positions and relationships between the different cameras, most of the time these calculations are not done manually. And so usually these motion capture setups have some kind of software that kind of automatically kind of calibrates, the relative positions of the cameras and what that means for the positions of the trackers. Okay. So a lot of times you're not doing these calculations yourself. They're usually built into whatever software that you're using. Okay. All right. So, most setups nowadays, if you have enough cameras and they're of good quality, the measurement precision is actually pretty accurate. And so usually the precision is within a couple millimeters. Okay. Interestingly enough, the biggest source of errors in mocap setups don't really have anything to do with the cameras or the markers. It has to actually do with the subject of the motion most of the time. So a lot of times, these markers are often placed on locations that that may be attached to some kind of muscle or maybe some kind of fat on the person. And just the fact that soft tissue is not rigid and it can kind of move kind of unexpectedly during the motion. This is actually kind of what leads to most errors in mocap. Okay. So you can try to minimize this. So you can try to put the markers on, places that are fairly rigid. So places where your bone is very close to the skin. So those are going to be pretty rigid. But because, skin will naturally stretch, fat will naturally kind of jiggle, muscles will naturally kind of ripple. And so, there's some errors that are associated with that, but, you can try to minimize it as much as you can. Okay. The suit itself, if it's not tight enough, it can kind of move around as well. Yeah.
So just curious, you know what the tolerance is on the measurements?
They're within a few millimeters, and so if you set it up pretty well, so most setups are going to get you pretty good readings of the trackers, and so it kind of depends on the fineness of the motion that you want to track as well. And so arm motions, leg motions, torso motions, those are you pretty much get those perfectly. But if you want to track fingers, that might be a little more difficult because it's a bit more fine. Yeah, you might use a different setup for that too. You might bring the cameras a lot closer for something like that. Mhm. Okay. Let's see. Okay, so one other thing that you can do. So if you're interested in just positions, mocap does a pretty good job of this. But oftentimes in biomechanical analysis, you're also interested in things like velocities and accelerations as well. And so of course, one way that you can compute velocities and accelerations is you can just take the derivative of the positions and that will give you velocities. So that is possible, but the thing with these position signals is that even though the tolerance is pretty good, they can be a little bit noisy as well, right? Especially when you're doing a complex motion that's where the markers are being obscured on a regular basis. You have to go between different camera views. The noisy signals basically means that it's hard to take derivatives. Right? So there's some signal processing that you can do to help with this. And so you can take your position signal, you can smooth it a little bit. So that can help, but user beware. So if you're going to take derivatives of any kind of noise signal, it's always going to be tough. And so nowadays, what's more common is to combine motion capture with some kind of inertial trackers. And so, last time we talked about, accelerometers that are often, in our phones. Those are often combined with these tracking signals so that they can independently track velocities and accelerations. So we don't have to rely on just on the motion capture to compute those things. Okay. Well, that's kind of just the qualitative information of how motion captures are set up and kind of what how they kind of work. There's a lot a lot more that we can discuss here, and honestly a lot more that even I don't really know. For the most part, I'm mostly just aware of the basics. But there's a lot of really interesting things that we can talk about here as well. Any questions on this? Okay. All right, so let's bring it back to biomechanics. So how do we use this information? So to take tracking information or tracker information and to turn it into something that we can use for biomechanical analysis, we're going to go through a process called inverse kinematics. Okay. So in inverse kinematics, what we're going to do, or the goal, is to take kind of raw data from position trackers and transform them into, joint angle kinematics. Okay. So the way this works is, remember we talked about earlier that each segment of the body, we consider them to be a rigid body, okay? And so every single segment of your body, it's all going to move together, okay? One thing that you can do to a rigid body is that you can attach a local reference frame or a local coordinate system to that rigid body. Okay. Okay. And so the idea with these local reference frames is that they're attached to the body or attached to each body segment. okay? And as the body segment kind of changes position and changes orientation, these local reference frames will change along with it. And so, for instance, if we take, let's say the arm, right? So let's say we have the upper arm, the lower arm, and the hand, okay? We'll consider the hand to be all just one body, just for the sake of simplicity, okay? Okay, so for each of these body segments, we're going to attach a reference frame. And so for simplicity right now, we're just going to stick to 2D. And so to attach the upper arm, we'll have a reference frame X1, Y1. For the lower arm, we'll have X2, Y2. And then on top of the hand, we'll have X3, Y3. Okay. All right. So notice how the arms and the hand in this case are in the reference position. So all the reference frames here are parallel to each other. Okay. Okay. But then as the arm kind of goes through the motion, so let's just do something simple where we're just going to flex at the elbow, right? And so if we flex at the elbow, oops, stay consistent with the coloring. Okay. So simple flex at the elbow, that puts our arms in the positions like this. If I were to redraw the coordinate systems, they would be still attached to the box to each segment in the exact same orientation that they were before. Okay. So for the upper arm kind of stayed flat, and so it still has an X1, Y1 like that. But because now the lower arm is flexed upwards like this, right? Our coordinate system has also moved. So it's changed positions, and so it's moved positionally from where it was before to where it is now. But it's also rotating. Okay. Same thing for the hand. Okay. All right. So this is really useful to us because what we can do now, so let's say that we wanted to compute the angle at the elbow joint. Okay. So one way that we can compute the angle at the elbow joint is to compute the relative orientation between the x1 and x2 vectors. Okay. Okay. Because if you measure that angle, right, that angle between x1 x2, that's the same angle of that angle that we're interested in, right? Because we started out, right, in the reference configuration, the angle between the upper and lower arm was 180 degrees, right? And then if we move to this configuration, and we kind of superimpose the x1 vector on top, right, like that. Okay. Let me kind of move it to the left a little bit to make it a bit more clear. Okay. Then that same joint angle can be obtained by this angle right here. And this is the simplest case, right? So this is the simplest case in 2D, but in 3D, our motions here are going to be very complex. Not only that, we have to also track the center of mass for each body segment as well. Okay, so it turns out that when you have very complex motion with multiple degrees of freedom, that tracking these coordinate systems or tracking these reference systems It's kind of the most effective way to capture all the kinematics. So that's going to be our goal basically is, how can we take our, our motion tracking information, our tracker positions, we're going to use those things to define, first establish these kind of local reference frames, and then use that to kind of track the reference frames positions and orientations throughout the entire motion. Okay. Okay. So now our problem, with inverse kinematics is kind of narrowed down a little bit, right? So we kind of started with this problem statement of, how do we take raw tracking data and then use that to establish joint angle kinematics, right? Now our problem here is a little bit more clearly defined. Okay? So now our problem is, I made an error, erased it, I drew it again. It's, how do we go from raw tracking data we're going to go from raw tracking data, we're going to transform that into local reference frame data. Because if you can track the local reference frames, you can track the motion of the body. Okay. Okay. Any questions on this? Okay, good. All right, so let's kind of jump back to kind of the earlier parts of the lecture today, right? So, one of the first things that we talked about today was that to track a particular body segment, you need at least 3 non-collinear markers. Right? Okay. And maybe some of you at the beginning, that may have given you some pause, right? Because if we think of the body as kind of a collection of sticks, right? And in fact, most of the time I'm going to draw, people as stick figures, right? He's doing something weird with his hands. I try to make it more realistic to have him bend at the wrist, but now he just looks like he's doing something weird. You might have said, wait a minute, each body segment can be considered a stick, right? So, a stick you can track with just 2 markers. And so, why do we need 3 if we can track, if each body segment is a rigid body anyway, right? Then it should be sufficient to just use 2 markers, right? Well, in 3 dimensions, right? And 3 dimensions, we need that 3rd marker because we need to establish, both X, Y, and Z coordinate, coordinate directions. Or I'm sorry, let me rephrase that. So 3 markers, not even in 3D, even in 2 dimensions, we need at least 3 markers there to establish just, even just 2 coordinate axes. Okay. Okay. Because for a reference frame, you actually need 3 pieces of information. You need 1, you need a location of the origin. Okay. 2, you need the direction of the x-axis, or just your first principal axis. And 3, you need the establishment of the y-axis as well. right? And so generally what's going to happen, right? So let's say that you have a certain body segment here, okay? We have our three markers, just like that, okay? So to establish a reference frame, you need those three things. So let's say we make this tracker, this one specifically, this will be our origin. Okay. Okay. And so if this one's our origin, we have, at this point, we have the freedom to choose, which direction is going to be our X direction. So let's say that we draw a direct line from that tracker to that tracker. That's going to be our X axis. Then for our y-axis, our y-axis, we can't just choose this last line here to be the y-axis, because our y-axis needs to be perpendicular to that one as well. Okay. Okay. And so one way that you can establish the y-axis is that you can take, this vector here, so the vector between the origin, and let me give these trackers numbers. So we'll say the origin is tracker 1, this will be tracker 2, that one will be tracker 3. Okay. So our y-axis here needs to be perpendicular to both, the x-axis, and still be within kind of the plane of the body itself. Okay. So to establish the y-axis, okay. So what's the best way to come up with a vector that's perpendicular to another one? The best way is to take a cross product. Okay? And so we know from vector algebra that, if we take the cross product of two vectors, we take vector 1, cross product with vector 2, okay? This is going to give us a third vector, vector 3, okay? And by properties of the cross product, this vector 3 is going to be perpendicular to both of the input vectors. So it's going to be perpendicular to both v1 and v2. Okay. So one way that we can come up with a y-axis here is that we can take the vector from 1 to 2. Okay. And if we take a cross product of that vector between, let's say we take another vector between 1 and 3. Okay. This will give us some new vector, vy. Okay. But then vy is going to be perpendicular to both vector 1, 2 and vector 1, 3. Okay. So we can use this to establish the, our y direction here. Okay. But we couldn't get that without this third marker. Okay. Okay, so that's why we need 3 markers there. So we need, we need a third marker there to establish, fully our coordinate system. Okay, it has the origin, the x-axis, and the y-axis. Okay. All right, and in 3 dimensions, actually, you actually don't even need an extra marker there, because then your final axis there, the z-axis, just needs to be perpendicular to both the x-axis and the y-axis. But now that you have your x and y-axis established, you just take the cross product between those two, and then that's going to give you your z-axis. Okay, so even in 3 dimensions, you still only need 3 markers to establish this. Okay. All right, any questions on this here? Okay, good. Okay, so how do we actually do this, right? So from that last example, you can kind of see that, the locations of the markers, they change kind of the nature of the reference frame or the coordinate system that we are going to establish. Okay. Okay. Usually, for these tracking systems, at least one of the markers, well, it has to be one of the markers. One of the markers is used to establish your origin. And so that is already always a kind of principal importance of, where is your origin going to be for each body segment. Okay. And then, usually the x-axis or one of the axes it's just a direct line from your origin to another tracker. And the other ones are established based on crosstalk. So where you place the markers, it's going to change the nature of your coordinate systems pretty heavily. Okay. And so because of that, there is some rules of thumb, that are used to establish where to place the markers. Okay. Because generally speaking, because, we have the freedom to kind of choose where we want these coordinate axes or reference frames to be established, usually we want to put them in a way that's kind of convenient for our calculations. Okay. Okay. So one guideline or one kind of rule of thumb that we like to do is we like to establish our coordinate systems in a way so that one of the principal axes kind of aligns with the bone that's in our body segment, or kind of aligns with the main axis of that body segment. Okay. So I think this is kind of most easily visualized for the arms and the legs. So for the arms and the legs, you have one main bone that kind of runs right down the middle of that segment. And so most of the time, we want to align one of the principal axes along this width. Okay. So, that's pretty straightforward. And that's kind of naturally what we've been drawing kind of up here as well. Okay. Another kind of rule of thumb is that we like to establish the origin close to the center of mass of the body segment. That's kind of, the natural thing to do. And you'll see later on too, once we get to inverse dynamics, it's gonna make some of our computations easier as well. If we kind of compute things around the center of mass. So when we compute rotations and moments and, angular accelerations, angular velocities, establishing that center of mass is critical. Just because it helps eliminate some terms in our moment equation. Okay. Okay. And so, generally these guidelines are pretty easy to follow. There's also, some kind of soft guidelines as well, where, you want to avoid putting markers on some bony segment, or you want to avoid putting them on places where the soft tissue can kind of move a lot. And so you want to put them where the bones are kind of clearly established. And so by doing so, you can establish what's called the anatomical reference frame. And so I'll shorten that to AF or ARF. Okay. So I'll be referring to that a lot. Okay. Okay. So for instance, if we were to look at the leg, okay. So, maybe this will be like the upper leg, this will be kind of the lower leg here. Right. The anatomical reference frame here, may look something like this, okay? So you can see here we have two trackers on the front and the back of the knee, okay? And this is a little bit cut off, and so, the thigh is was further than this, but we can use, maybe this one as the origin here. Okay. We have kind of one axis here that kind of goes right down the length of the leg. Okay. Okay. So all that makes sense, right? And so, eventually if we're going to be using these reference frames to track, the movement of these body segments, it makes sense to align it with the anatomy. Okay. All right. Any questions on this? Okay. Good. All right. There's one problem with this though. Okay. The problem with anatomical reference frames is that a lot of times, in order to establish an anatomical reference frame, the trackers have to be placed on some not so convenient locations. Okay? And so what I mean by that is that, these trackers are often obscured or often blocked from all the views of all the cameras. Okay? Okay. And so if you look at this example here, right? So we have one tracker on the front of the knee, one tracker on the back, right? It's really hard to get an exact camera angle that's going to capture both of those trackers at the same time, even though those trackers are really convenient for establishing the anatomical reference frame of the upper leg. Okay. And so, if you try to do a motion capture study with just the anatomical reference markers, you're going to have a lot of gaps in your data. Just because, there will be certain positions where, you're just going to completely lose one of the trackers, okay? Okay, and so to remedy this, oftentimes when you do a motion tracking study, you'll actually use multiple sets of markers on the same body segment. So one thing that's easy to track on the upper leg is, maybe you just put a set of 3 markers, right on the front of the thigh, right? So maybe you have 1, 2, 3, just like that, okay? Right. Unlike the anatomical reference frame, you don't have any limitations of, you have to span the entire body segment or you have to connect one axis, right down the length, right? The tracking reference frame, which is kind of what this is called, you want to just make sure that this is as visible to the cameras as possible. So you have a set of 3 markers that are, that can be tracked all throughout the motion. Okay? So this reference frame is limited only by the camera angles. Okay? So oftentimes you'll actually see, 3 markers that are, relatively, packed close together, just because they're in a really convenient location that can be tracked. Okay. And so this reference frame here in blue, this is often called the tracking reference frame. Okay. Okay. So we have our two reference frames here. Let me give this an acronym as well. So this is be the TRF. Okay. So we have one reference frame, the anatomical reference frame that's used that, aligns well with the, aligns well with the body segment, right? And so the anatomical reference frame, or the ARF, okay, we can use these to compute joint angles. Granted, we can see them. So if we can track the ARF, we can use these to directly compute the joint angles between the different body segments. Okay. But the problem with ARFs is that they are usually not tracked very well throughout a motion, especially if you're going, you're doing, maybe, I think this is most common in sports medicine, where they're tracking, certain motion of like a jump shot maybe, or maybe certain someone sprinting, right? The anatomical reference frame, oftentimes you're going to lose some of these markers throughout the motion. Okay? So the ARF is good for computing joint angles, but cannot be easily tracked. Okay? Whereas your TRF, the TRF is easily tracked, and so you have full freedom to kind of choose wherever you want to place these markers. And so if your cameras are kind of all set up in a certain way, you can put the trackers on there to make sure that they're always on camera all the time. Okay. Okay. The problem with TRFs is that oftentimes you're just going to place them all kind of close together in view of the camera. So the reference frame that you get from the TRFs are oftentimes kind of wonky. Okay. And so because of that, it's really hard to compute joint angles with them because the x-axes for neighboring segments are often going to be in different directions. So which one do we use, or how do we use these two ideas to get what we want, right? So we want to be able to compute the joint angles, track them accurately, and use them for analysis, but we want to make sure that we track them all throughout the motion. Okay. So what's usually done, or kind of the industry standard, is to use both actually, and so you're going to use you're going to establish both an ARF and a TRF on the same body segment. Okay. So that could mean up to 6 markers on a body segment, although sometimes there are certain markers that can be used for both the ARF and the TRF. And so it's on a, and so you might have a marker that's on a boning landmark that is very easily tracked by the camera. Okay. But you have to establish both these systems. But once you have both of these systems established, you kind of take advantage of the fact that, even though the person's body may move, right, the relationship between the ARF and the TRF remains static because, the trackers are not moving relative to the segment itself. Okay? So let me say this. So since the relationship or the relative positions, okay? So the relative position and orientation of the ARF and TRF is constant because they're attached to the same body segment. Okay. If you can establish that relationship, or if you basically know how to take something from the TRF and transform that into the ARF, then then you can use these two kind of in tandem. Okay? And so what's typically done is that when you start a motion capture study, you do a step called calibration. Okay. And the idea with calibration is to establish the mathematical relationship between the ARF and the TRF for each body segment under consideration. Okay. So basically what you're going to do is that you're going to ask the person to kind of move their bodies in a particular position so that you can see all 6 markers. So all the markers of the TRF and all markers of the ARF, they all need to be on at least 2 cameras at the same time. Okay. And the mathematical kind of manifestation of this is something called a transformation matrix. And so actually, for those of you in my finite element class, we're actually going over transformation matrices there as well, although in a very, very different context. And so, you'll see a little bit of a repeat. And so, you'll see that here as well. But basically, the idea with the transformation matrix is that if you have coordinates or you have a vector and that's established in one coordinate system, if you multiply that by the transformation matrix, you get the same vector coordinates in a different coordinate system. Okay. And so transformation matrices are how we're going to basically, jump around from one reference frame to another. And that's exactly how we're actually going to compute joint angles as well. So transformation matrices are really key to this whole concept of, human motion kinematics. Okay. All right, any questions on this? Okay, but we're out of time today, so we'll start doing transformation matrices next time. So we'll go over kind of the idea of transformation matrices, and we'll do a couple of examples. So get your trigonometry hats on for Wednesday. So thank you guys for coming today. I hope you guys have a good rest of your day. It looks like it's going to rain out there, so make sure you guys are staying warm, staying dry, staying safe. So I will see you guys on Wednesday. Yeah. So, kind of this problem is, if you were to walk or run at it's kind of really. And so it's kind of the best thing to do. You have the other distance cover and to, you don't need to sprint the entire way, drop the car and walk the car. And so this cost has that kind of question. If you were to run, I think you know, walking speed 1.3 meters per second, running speed 3.8 meters per second. So those are your 2 speeds. And so if you were to, if you need to travel 2.5 kilometers, so quite a bit actually. You have 15 inches to it. What's the most amount of seconds? So the way you can do this is that you can, from 1 meter, take the distance, so 2,500 meters, divided by the time. So that's going to give you the average to walk side. It's going to be something between 1 area and this class. And so based on that, what ratio 1.3 1.8 is going to be for a second. So let me show you. So So one way to kind of set this up is that, let's say that X here represents the percentage of time that you're going to be walking, right? Okay, and so if you do, let's see, so if you do 1.3, because that's your walking speed, right? You multiply by X, okay? And your running speed is 3.8. So for every time that you're not walking, you're going to be running, right?
Yeah.
And so if X here is a percentage, then the percentage of running is going to be 1 minus X, right? And so if you set this equal to the average speed, right? You solve for X, that's going to give you this number right here. Yeah. And then the percentage of running is going to be 100% minus that, which is just that. Yeah. So there's a little bit of extra information here. So, I gave you the energy expenditure just kind of for fun.
Yeah.
And so, I gave you the weight. So you can take that and you can compute, the energy, the power expenditure too. But this problem just specifically asks you for percentage of walking, percentage of.
Okay.
Yeah.
I think that's where I'm confused. I'm trying to figure out how to incorporate like energy into that. So
Yeah, you can. It's just kind of stuff. You just there's a way that you can do it with the energy, but this I think is the simplest way to do it.
Okay. That makes sense.
Mhm.
Thank you.
Yep. Hey,
I don't want to take up too much of your time, but I had a question about the homework.
Sure.
It's problem 3,
okay.
and it's when it comes to the graph. So I noticed like the shape of it looks like your solution.
Mhm.
The only thing I noticed is that I'm getting negative values
Mhm.
here. So I'm wondering if maybe if you could just like see if this equation looks correct.
Let's see. Yeah, nice and big.
You on Wednesday?
Right. See you Wednesday. Oh, sorry. Yeah, these look correct here. So you do chain rule. I may have just made it positive just because it's I'm just doing force and magnitude. I think that's probably what I did.
Okay,
But yeah, but your equations look right to me.
okay.
I need to go back and check my code. I think I just made it positive just to make it force magnitude. But
Oh, I see.
Yeah. Mhm.
Okay, well, thank you.
yep. Mhm.